So let's take a look at what Newton knew. He knew what the acceleration due to gravity was at the surface of Earth. He also knew what the orbital distance to the moon was. It was 384,000 kilometers, but it's also almost exactly 60 Earth radii. He also knew what the orbital period was of the moon, and on top of this, he knew the orbital behavior of Mercury, Venus, Earth, Mars, Jupiter, and Saturn around the sun. So he took all of this information and put it together to try to understand the forces that were involved in causing the motions that were going on in the solar system. And for now, we're going to go and do some numbers with him. So when you look at the moon's orbit, it looks like it's basically a circle. And if you have something that's going in a circle, then you have a centripetal acceleration. So the centripetal acceleration for the moon, you would find the same way that you find the centripetal acceleration for anything, which is v squared over r. The velocity for the moon is going to be 2 times pi times its orbital radius divided by the amount of time that it takes to get around its orbital period. And that is going to be 2 times pi times 3.84 times 10 to the 8th meters over orbital period. The moon is 27.32 days, but that's not a particularly useful unit, so 86,400 seconds per day to turn that into seconds. And you find that the velocity for the moon is 1,022 meters per second. So you work out the centripetal acceleration for the moon, and that becomes v squared over r, 1,022 meters per second squared, over its distance from Earth, again, 3.84 times 10 to the 8th meters. Now we're assuming that this is a circular orbit, which strictly speaking isn't actually true, but it's close enough. And when you work through this, you find that the acceleration for the moon is 0.00272 meters per second squared. Now that number doesn't look like too much, but if you look at the gravitational constant at Earth's surface, that's 9.81 meters per second squared. And that's at 1 Earth radius. The acceleration for the moon is 0.00272 at 60 Earth radii. And if you divide the acceleration due to gravity at the surface of Earth by the acceleration of the moon, the centripetal acceleration, you find 0.0272 about 3,600. 3,600 is the square of 60. Coincidence? I think not. This looks like a force that's diminishing with the square of the distance. All right, so when you look at the simulator, you can look at the motions of all the planets that were known in Newton's time. We could show all the solar system orbits and the planets. And when you look at this, you can see that Saturn here is really lumbering around the sun. Jupiter, not so much. And the innermost planets are definitely going faster. So, take a look at Mercury, Venus, Earth, Mars, Jupiter, and Saturn, and decide which of these planets has the greatest speed, and which of these planets has the greatest orbital radius. And if you have a combination of things like a small orbital radius and a high speed, like Mercury, then you're going to have a very large centripetal acceleration. All right, so now we're just looking at an orbit that's a perfect circle at the orbital radius of Earth, which is 1 astronomical unit. You can go through and compute v squared over r to determine what the centripetal acceleration of Earth is, or you can just take this thing's word for it. And you can even see that, yes, that is a center-seeking force acting on this that is causing an acceleration towards the center. Now, when you look at something that is 1 AU away, you see that the acceleration is 0.00593 meters per second squared. And you can reset this to something that's a tenth that orbital size. So now this is only 0.1 AU away from the sun. And when you look at it, you can tell that this thing is definitely going really, really fast. And so we can slow it down to something more civilized. But when you look at the centripetal acceleration for this one, it's still the 593, but it's 0.593. This is now a factor of 100 greater than the centripetal acceleration for something that is 10 times farther out. Again, you're seeing this 1 over r squared relationship between the distance of an object from the sun and the acceleration due to some mysterious force. So let's see how we can tie this back to Kepler's laws. We're looking at, effectively, circular motion. There's our sun, and something orbiting around it in approximately a circle. And that something has a speed, v, and it has a distance from the sun of r. Now, as you know, velocity is just the distance divided by the time, and the distance that this thing would cover in one full orbit would be 2 times pi times r, and the amount of time that it takes for it to do that is considered to be its orbital period p. So velocity is 2 pi r divided by p. When you look at the centripetal acceleration, you find that that is v squared over r, but Newton realized that that is proportional to 1 over r squared, that whatever is causing the motions of the planets is following a 1 over r squared relationship. What that means is the velocity squared would be proportional to 1 over r, but from up here, we also find that the velocity squared is 4 pi squared r squared over p squared. So now you have these two terms that are the same, and when you do some rearranging, you find that r cubed over p squared is proportional to 1 over 4 pi squared. What that means is that you've just found out Kepler's third law, which says that the semi-major axis, which is essentially the orbital radius, cubed divided by the period squared is equal to some constant.